All right, let me go ahead and start. So the last two lectures we did on inductors, we're going to revisit inductors and capacitors from the perspective of AC as opposed to direct current, which is what we've been dealing with this whole time. So how inductors behave when it comes to applying like a sine wave for alternating current. We're going to look at that later. But the last two lectures, we dealt with inductors from the perspective of a non changing current, except we did have a switch that opened and closed because to see it build up that magnetic field and oppose the change in current. We're going to also look at capacitors today, which is a new type of component. We're going to go ahead and look at those from a very similar perspective. We're going to look at it from a non-changing current. Yes, I am recording currently. And we're going to look at capacitors first from that DC perspective. Then we'll cover AC and we'll revisit the inductors and capacitors and we'll build upon from there. So, okay, what exactly is a capacitor? So, if you go ahead and look at the basic construction of what a capacitor is, you form one by having two conductors separated by an insulator, or we're going to call it a dielectric. So if you look at any basic capacitor, we have one terminal which connects to a plate, a conductive plate. And then we have another conductor on the other side and that other conductor connects to the other terminal. So this is a two-terminal device. We have two wires coming off of here. And we have these two conductors that are separated by an insulator. We call this a dielectric. Now, what's the idea behind this capacitor? Well, capacitors store electrical charge when a voltage is applied. Okay, so in this case, if we were to apply a voltage, what's going to happen is we will get current to flow, and we're going to build up positive charge on one of these plates. And on the other plate, we're going to end up with negative charge. So we're going to end up storing energy in this guy. Now, when you looked at an inductor from the last two lectures, we stored energy as well, but we stored it in a magnetic field. Whereas for a capacitor, we're going to be storing energy very similar to an inductor. However, instead of a magnetic field, it's actually going to be charge that builds up on these plates. So on this side, we're going to get an excess of electrons, and on this side, we're going to end up getting a lack of electrons. And so we end up with positive charge on one side, negative charge on the other side. Now, once this capacitor is charged, essentially it's going to act like a battery. It's going to have energy stored in it. We're going to be able to get energy out of it. We're going to be able to do work with the charge that gets stored on these plates. Okay, so from a very basic level, capacitors store electrical charge when a voltage is applied. Now, when I talked about inductance, I said inductance opposes a change in current, and resistors oppose the flow of current. Inductors oppose a change of current. Capacitors, I'm going to make a similar statement about capacitance. Capacitors oppose a change in voltage. Okay, and the reason I say it's going to oppose a change in voltage is because let's say we were applying some voltage to this capacitor. It's going to take some time for this capacitor to build up the voltage. Okay, so let's go ahead and let's talk about the schematic symbol, and then we can see about this change in voltage. Okay, we're going to have two schematic symbols for this capacitor. There are two fundamental types of capacitors that are constructed, and their construction techniques are vastly different. And so we're just going to have to live with this, that there's two different schematic symbols to refer to a capacitor, but they are essentially the same. Okay, so the first schematic symbol let's look at, this is the pure capacitor, the ideal capacitor. We just have two plates that are connected in our circuit somewhere, and it's separated here. You can kind of see that implied in the schematic symbol, that they are not electrically connected to each other. They are separated by this insulator. So from the physical construction of a capacitor to the schematic symbol, they do kind of correspond. You know, we have these two plates that are separated by a gap. And we also have this second schematic symbol for a capacitor, which one side we've made it curved, and there is a polarity associated with it. Now, this is just an artifact of construction, meaning for this capacitor to physically be realized, we need to pay attention to the polarity, meaning we always want this side to be the higher voltage, this side to be the lower voltage, and the capacitor will function. Now, if we were to reverse the polarity, meaning if we had this bottom side attached to the higher voltage and this was the lower voltage, the cap will still work for a period of time, but eventually it's going to break down. And that's not because capacitors require having polarity, but it's because of the type of capacitor you have to deal with some physical limitations, and so we're required to actually connect it such that the higher voltage is on the flat side and the curved side has the lower voltage. Now, these are two different types of capacitors. When you see a symbol that looks like this, generally speaking, this is a ceramic capacitor. And when you see that we have polarity, this is referred to as an electrolytic capacitor. Okay, and I have some examples here. So as far as ceramic capacitors, they're going to look like this. Little guys, usually some kind of flat disc, maybe colored, but generally speaking, these are your ceramic capacitors. Now, electrolytic capacitors, they can actually store quite a bit more energy than their ceramic counterparts. But that's why the construction has to be different. What they're doing with these capacitors is they actually, here's an electrolytic. What they actually do is they take two foil strips, they separate it with a dielectric, think of like a piece of paper, and then they roll it up into a tin can, and we have an electrolytic capacitor. Here's another electrolytic capacitor, quite a bit more. You can tell that the larger one should be able to hold more energy inside. So we just have larger conductors that allow more charge to develop on these two plates. Okay, so ceramic capacitors are lower in value of this capacitance. So capacitance is how much charge we can store. Or electrolytic, which you can store a lot more. Now, as far as the biggest capacitor that I have laying around, yeah, this is like the size of my fist. This is a big cap.
What can you even use for?
For filtering large for filtering large voltage changes across something. But yeah, you're right. No typical electronic circuit is going to use one of these. This is more for large industrial power applications, motors, things like that. But yeah, generally speaking, the caps you will encounter are like this, but they do get quite large. Okay, now for all practical purposes, on the board in our circuit simulation tools, these are really both the same. It really doesn't matter. We're going to treat all capacitors like this. You really only care about the polarity when you're talking about actually constructing a circuit and you need a certain value and you decide you are going to use an electrolytic capacitor, and now I need to connect this into a circuit that I'm going to construct, and now you do care about the polarity. But until that point, until you physically realize a circuit, there's no reason to concern yourselves with the polarity. This is more of a practical type of thing. These two capacitors are essentially the same thing, and we can think of them as your ideal basic capacitor. Okay, there are some caveats about using one of these versus another. There's other things that come into play, but we really don't have to concern ourselves with that at this point. Okay. So let me go ahead and say has polarity. Whereas this one does not. So this ceramic capacitor does not care whether I plug it into my circuit this way or if I flip it around and plug it in the other way. This one will actually work if you have it reversed, but it will die out rather quickly. Probably go up in a puff of smoke and let out the magic smoke. Okay, so let's go ahead and let's put up a simple schematic with a cap. So at this point with our circuit open, we would have no charge built up on these plates. Now, once we go ahead, let's say this is a 10-volt voltage source. Once you go ahead and close this switch, we will start to get current flowing on here, and we will start to develop some charge on these plates. We will have less than 10 volts. Now, after some time, which we're going to need values in order to express how long it's going to take for this to happen. After some time of this building up charge on it, this will actually get 10 volts across it. At that point, you've put as much charge as you possibly could on this cap, and it cannot build up any more charge on it. Physically, these plates are only so large. I can't just keep on dumping an infinite amount of charge onto these plates. At some point, the electrons are squished together along this plate, and I just can't put any more onto it. But at that point, when I do have as much charge as the cap could possibly get on it, I will have 10 volts across the cap. In other words, this cap is going to be charged all the way with 10 volts across it. Now, if I go ahead and now after the cap has been charged, if I go ahead and open the switch again, this cap is still going to have the charge built up on the plates. In other words, V sub C, the voltage across the cap, is still going to be equal to 10 volts. We have nowhere for this charge to go. Okay? It will slowly dissipate over time. Generally speaking, we don't worry about that. We treat this very much as though it's a small battery that has the potential to give us 10 volts out of it. Okay? And that's with this being open. So you can see that this cap actually acts as a temporary storage of charge. Okay, so we can think about this like a battery that can charge and discharge quickly. And this ends up being a very useful circuit element for us to be able to use, especially when you want things to take some amount of time because the charge does not build up on this instantly. And you can also use it as an energy storage device to act like a temporary battery, and you can get a lot of useful functionality out of that feature about a capacitor. Now, what we need to do is describe how much charge we can actually store on this. You can quite literally think of this as a number of electrons building up on this plate. You know, in this point we have no electrons, and at this point we have applied a voltage and we've built up the charge on the plates, and now we have some number of electrons built up on here. Now, to describe how much energy you could store in this capacitor in order to quantify how much charge you would build up on it, we have the unit of capacitance, which is known as the farad. This is named after Michael Faraday. That's where we get the name farad. We named the unit of capacitance, and by we, I meant 200 years ago, 100 years ago, someone much smarter than me developed this, understood it, and quantified it, and named it after him. Now, in order to describe what a farad is, there's a pretty useful sentence to do this. 1 farad is the amount of capacitance where a charge of 1 coulomb develops a potential difference of 1 volt across the cap. And I'm going to go ahead and I abbreviate the word capacitor as cap all the time. And most people do. So just bear with me. I'll be saying cap. Okay, so what does this mean? Well, if I have a 1 volt source that has built up one coulomb of charge, and remember a coulomb's equal to some number of electrons. So if I develop 1 coulomb of charge on this cap when I have 1 volt applied to it, then this cap equals 1 farad. Okay, now a farad is actually quite a lot of charge. For reference, my giant cap over here is 5,500 millifarads. Okay, now this is a giant cap. Generally speaking, this would be a large cap in most circuits, and this is actually 100 microfarads. This cap over here is 100 microfarads as well. However, this capacitor can safely do 350 volts, whereas this one can only do 25 volts. And if I go to one of these smaller ones, these ceramic capacitors, this is actually 10 picofarad, which is a much, much smaller. Pico is 10 to the minus 9. No, 10 to the minus 12. 10 to the minus 9 would be nanofarad. I need to remember cap equals capacitor in your vocabulary rather than the one you are wearing on your head. Oh, cap. That's funny. Actually, I hear the word cap. I don't even think of a hat that goes on someone's head. I think of capacitor. Okay, so microfarad is 10 to the minus 6, nanofarad is 10 to the minus 9, picofarad 10 to the minus 12. That is a very small amount of capacitance, but look at how physically small this cap is versus something like that. Okay? But generally speaking, farads as being the base unit, we don't encounter a farad of capacitance very often. That's actually quite a bit of capacitance. Okay, and now we have a relationship between capacitance, charge, and voltage. Okay, so capacitance equals charge divided by voltage. C is capacitance in farads. Charge is coulombs. And V, of course, is voltage. Okay, so if we were to take a 12-volt source and apply that to a rather large capacitor that has 10 farads, how much charge have we stored on this capacitor? Well, you just plug it into this very simple relationship over here. And you get 10 farads is equal to Q divided by 12 volts. And so Q ends up being equal to 120 coulombs, which is a lot of charge. Okay, so that's how you quantify the storage ability of a capacitor. Now, let's look at what happens when we put caps in series and in parallel. I like to do caps in parallel first. And let's say let's use some more reasonable values for these capacitors. Let's do 5 microfarad and let's do 10 microfarad. Well, capacitors in parallel are actually going to add. So you're going to flip that relationship that you know about resistance. Resistance in series adds, however, caps in parallel add. And if you think about this, if I'm applying the voltage the same to each one of these, it's almost like I have one capacitor with a physically larger 2 plates if I put them in parallel. So we can count on capacitance in parallel to add. So C total, or the total capacitance, is going to be equal to C1 plus C2 plus ... however many capacitors we have all the way to Cn. And so we're going to end up getting a total capacitance that's equal to 5 microfarads plus 10 microfarads, which is going to be equal to 15 microfarads. Okay, because capacitors in parallel will add. However, caps in series if I go ahead and take 2 caps in series, I'm actually going to get less capacitance. Caps in series are going to behave kind of like resistors in parallel. It's the same equation. We get 1 divided by the summation of all the inverses of the capacitance. So you get 1 over C1 plus 1 over C2 plus ... plus 1 over Cn. Or for 2 caps in series, we can go ahead and say that CT is going to be equal to C1 times C2 divided by C1 plus C2. So it's that same equation that we used for resistances in parallel, but it applies for caps in series. Okay, so if I were to have 2 of these, and let's say they are 2 microfarads each, then I'm going to end up getting 1 capacitor, or I can reduce it to be a total capacitance that's equal to, well, 2 microfarads times 2 microfarads divided by 2 microfarads plus 2 microfarads, which is going to be 1 microfarad. Now, if we're talking about the voltage distribution among these caps, well, the same rules that we had earlier in the semester have never gone away. Things that are in parallel will have the same voltage drop across them. So if I have 10 volts over here, I'm going to have 10 volts across this cap once it's fully charged, and same thing over here. I'm going to have 10 volts across this cap once it's fully charged, because both of these capacitors are in parallel, and they're all in parallel with a voltage source. However, the voltage distribution will change if I have caps in series. Now, what we're going to find is the voltage across any given cap is inversely proportional to its capacitance. Or you could think about it as just being inversely proportional to the number of farads that are on it, its C value. And what we can say is the voltage across any given cap, I'm just using X to say C1 or C2 or C3, the voltage across that is going to be equal to the supply voltage times the total capacitance divided by the capacitance value of the one we want to find the voltage for. So let's do an example of this. Let's go ahead and say we have a source voltage equal to 90 volts. Let's put two caps in series. And let's say that C1 is equal to 3 microfarad. And let's say C2 is equal to 6 microfarad. And now I think a logical question would be, well, how much voltage is across the first cap and how much voltage is across the second cap? We can use this to figure that out because it is inversely proportional to its capacitance. Okay, so what we want to find out is VC1 equals what? VC2 equals what? Well, first we need to figure out what the total capacitance is so we can plug it into our equation up there. CT is going to be equal to, well, since we have two caps in series, we can go ahead and say 3 microfarad times 6 microfarad divided by 9 microfarad. You're going to get 2 microfarad for what the total combined capacitance is for these two caps in series. And then if you want to figure out how much voltage is across the first cap, we can say VC1. So I'm just replacing the X with my first capacitance since that's the voltage we're trying to find. The voltage across C1 is going to be equal to, well, our total applied voltage to the series combination of these capacitances, or the series combination of these capacitors. You're going to get VC1 equals 90 volts times the total capacitance, which is 2 microfarad, divided by the capacitance value we're looking for, which is going to be 3 microfarad. What you're going to get is 60 volts. So we developed 60 volts across the first cap, Now the second cap, you would suspect that Kirchhoff's voltage law holds true here. And so 90 volts minus 60 volts gives us 30 volts. I think it's going to be 30 volts. Well, let's go ahead. Let's calculate that just to be sure of it and make sure everything agrees with each other. VC2 is going to be equal to 90 volts times 2 microfarad divided by 6 microfarad, because we're looking for the voltage across the second cap, and it has a capacitance of 6 microfarads. And so you're going to get, surprise, surprise, 30 volts. Repeat how Cx is found. Well, those were given. So the amount of capacitance for this first capacitor was given as being 3 microfarads, and the second capacitance was 6 microfarads. Yeah. If I choose a cap, it tells me how many microfarads it has on it. On a ceramic cap, it actually gives it to you in a default value of picofarads. So like this one, a little hard to see. There's a 1-0. That's 10 picofarad. They don't have enough room to actually write out the units on it. Okay, so the voltage distribution in series caps just requires the extra step of calculating the total capacitance and then multiplying the applied voltage by the ratio. Whereas when we did it for being in parallel, it is so much easier because, well, they're just in parallel. They should have the same voltage drop across them. Okay, so let's see. We started at 9:30. We're at 9:43 right now. I'm debating whether 8 minutes is enough time to go into the universal time constant chart.
I don't know if this is going to make a difference, but it's 10:13, not 9:43.
Oh, sorry. I meant 10:13. Yeah, I must have. I looked at the clock. Mine does say 10:13 right now. I just misspoke and must have said 9:45. Okay, let's go ahead and let's look at a real simple example. Now, when we put a resistor in series with a capacitor, you're limiting the amount of current that can flow through this capacitor. And what's going to happen is we're going to develop charge across this cap, but it's not going to develop instantaneously. It's going to take some time to build up the charge on this cap. And so the question would be, how much time is that going to take? And we can actually use the same universal time constant chart that we used for the inductors. We can use that for talking about how long it takes for the voltage to actually equal the voltage that's applied. And let me go ahead and draw that universal time constant chart here. And so it's going to take, very similarly to inductors, it's going to take 5 time constants in order to reach our max value. So 0 time constants, 1 time constant, 2 time constant, 3 time constants, 4, and 5. Now, at the first time constant, we actually reach 63.2% of our max value. So if you think about the 50 mark, well, let's say over here, let's call this 100% first. We're going to reach 100% after 5 time constants. Now, what is a time constant? Our time constant is equal to R times C. So whatever the resistance value here, if this is 100 ohms, it's going to be 100 times however much capacitance we have, however many farads this capacitor is. The larger the amount of charge we can store on this cap, the longer it's going to take to reach this max value. But it's always going to be 5 times the RC time constant. Now, our 62% happens at the first time constant. At the second time constant, we reach 86.5. Three, 4, and then 5. And we get this exponential curve. Okay, now this just refers to our percentage of max value, but what is our max value as far as a quantity is concerned? This is the voltage across the capacitor. So we know before we throw the switch, we have 0 charge stored up on this cap. Hence, we will have 0 volts across this cap. But once we go ahead and throw the switch and close it, we're going to start developing charge on this cap, and so the voltage is going to slowly rise. So how do we figure out how long that's going to take? We can use the time constant RC in order to tell us that. So if we had, say, 10 volts, well, our max value is going to be 10 volts over here, where we start at 0% of our max value, which is 0 volts. Okay, and then after 1 times the RC time constant, let's go ahead and give ourselves some values here. Let's say R is going to be equal to 100 ohms, and let's say our cap, let's keep this real simple, let's say our cap is 1 farad. Okay, so what is our time constant? Our time constant is going to be 100 ohms times 1 farad. (100 seconds is 1 time constant. because our answer is always going to be in base unit of seconds for time. And so this first time constant happens after 100 seconds. Our second time constant, 2 times our time constant, would be 200 seconds. 300 seconds, 400 seconds, 500 seconds. Okay, so it takes a full 500 seconds for us to finally reach 10 volts across this 1 farad cap when we have 10 volts applied to this circuit. So at time 0, we start off with 0 volts across it, and then we end with 10 volts across it. Now, I'm going to go over the time constant chart in more detail next class. I think I'm going to cut this here. We got through all the basics and introduction to the capacitor. We'll go into how to better calculate this next time. I'll do a live example of charging a cap on my oscilloscope, and we can actually calculate the time constant. And you'll be able to see that in real time. But for now, let's go ahead. Let's take a 10-minute break here, and let's come back to lab. Sorry, I can't speak today. The inductor lab is going to be very quick and easy to do, and I'll walk everyone through how to do this in LT Spice with the inductor. And then we'll see the results of that during lab. And then next class we'll do a simple lab, which is going to mirror the example that I do during the lecture. Okay, except we'll just do it at home in a simulating capacity. Okay, so let's go ahead. Let's take a 10-minute break here. Okay, so let's go ahead and let's fire up let's open up LT Spice and let's open up that lab, and I'll kind of walk through how to do that. One other type of capacitor, and I just saw this, that I have this lying on my desk, is this old school parallel plate capacitor. This is actually done using plates. So this is quite literally that basic construction of having 2 parallel plates, except we have more parallel plates. And this one's meant to be adjustable because it is used to tune frequencies in a radio. And so the plates actually, if I have them closer together, I get more capacitance, less capacitance, less capacitance, less capacitance, less capacitance. And this is how radios. There's more clever, ingenious ways to do it these days, but this is how it used to be done. This is how every radio worked back, let's say 60s. 70s, yeah, even the 70s. You start getting diodes that can be used to tune the frequencies as opposed to mechanically having to increase the capacitance or decrease it. So let's go ahead, let's open up that lab document. I set the due date for this lab to be next class, just because I want to do the simple capacitor lab as well on Thursday. But this lab is very quick to do. So introduction to LT Spice and inductors. Go ahead and open that lab 7 document. Okay, so what are we going to do? We're going to hook up a 10 volt DC source and we're going to pulse that source. So that source is going to start at 0 and then it's going to go up to 10 volts. We're going to have a 10 ohm resistor in series with the inductor, and then we're going to have a 1 Henry inductor in series with the 10 ohm resistance. And what we know the inductor is going to do is it's going to prevent the instantaneous change in current. That's what we said about inductors. Inductance opposes a change in current. Resistors oppose the flow of current. Capacitors oppose a change in voltage, and we saw that how long it takes for that capacitor, that relatively large capacitor, to charge up. So we saw that it does prevent the instantaneous change in voltage. And inductance does the same thing but to current. It doesn't allow the current to change quickly due to that self-inductance, that mechanism where that inductor, as the magnetic field is increasing, acts like a temporary backwards battery that prevents the instantaneous change in current. So now what we're going to do is, using LT Spice, we're going to see that. So let's go ahead, let's open up LT Spice. Let's go File, New Schematic. And in here we saw we're going to want a 10 volt source. So I'm going to hit F2, scroll to the end, hit voltage, hit OK. And let's just place that voltage source down, escape to stop placing. I did see that somebody said, I really like how little time LT Spice takes to load up. I agree. I think software these days has gotten too bloated. There's too much stuff that's running in the background in your system tray, and it's all unnecessary. I like programs that are just straight to the point, give you the answers you want, and that's it. And LT Spice fits the bill in that category. There's other circuits, circuit modeling, circuit simulation softwares that are out there, and they're even based off of the same Spice engine, but they're bloated. LT Spice just gives me the answers that I want as quick as possible. And the interface, yeah, it's not intuitive at first, but the interface is so clean. Once you just learn 3 or 4 shortcuts, you can piece together your circuits so quickly. So now let's go ahead and let's put a, what was it, a 10 ohm? Let me close this. We're going to want a 10 ohm resistor in series with the inductor. So I'll hit R and I'll place a resistor here. Escape to quit out of that. Now I need to place an inductor. For inductor, just hit L. And you place an inductor, left click and hit escape and you're done. Let's go ahead and wire these all up. Voltage source connects to the resistor connects to the inductor, and the inductor goes back to the minus side of our voltage source. And for the LT Spice simulation to work, we're going to have to pick a reference node here that we call 0 volts. I'll just hit G, and that brings up the ground symbol. I'll left click at the bottom of my circuit, then hit F3 to change over to the wiring tool and connect that up. And now we have a voltage source, a resistor. We need to set the value, so I'll right click on the resistor and set that over to 10 ohms. The inductor, we're going to do the same thing. We need to set the inductor to be 1 Henry. So right click on the inductor, and for the inductance value, it's going to be 1 Henry. The default unit is H, so just put a 1 there and hit OK. Now, in order for this inductor to act more closely to an idealized inductor, we're going to set the series resistance of the inductor to be 0. Now, here's the thing. When I have an inductor in real life, here's an inductor. Whoa. It's nothing more than a coil of wire. Here's also an inductor. again, it's just a coil of wire. This one happens to be shaped in a toroid in order to constrain the magnetic field flux lines. And this is also an inductor. This looks like just a spool of wire. Now, wire, we've been ideally visualizing it on the board as having 0 ohms of resistance. But unless you're cryogenically freezing your wire, you're going to have some resistance. And so LT Spice tries to put that into the model by default. So since I want this inductor to behave more like an ideal inductor, I'm going to set its series resistance to be 0 ohms. So when you right click on the inductor, below the inductance value, you have peak current and you have series resistance. I'm going to put a 0 in there. If you notice the series resistance defaults, it tells you at the bottom of this window 1 milliohm of series resistance. So I'm just going to force that to be 0 so it behaves more like an ideal inductor. Let's hit OK. And now we need to set up our DC voltage source to act as a pulse. This inductor, if we just apply a constant voltage to it, it will behave just like a wire. In fact, if I do nothing here but just set my voltage source to be 10 volts and I hit run, well, I'm going to need to give it a stop time. For now, let's go ahead and just say 1 second. I get 1 amp through this thing, right? I get 1 amp through this all day long because there's no changing current. And an inductor opposes a change in current. So I need to cause a change in current. The way I'm going to do that is by setting up my voltage source to actually act a bit like a switch. It's going to start off at 0 volts, and then after 1 second, it's going to go up to 10 volts. So let's see, what does the lab say? Change the function to pulse. We want 1 second before the voltage goes high. In other words, before the voltage goes up to 10 volts. We want to wait at 10 volts for 1 second, and then we want the voltage to go back down to 0. Okay, so what we're going to have is a little bit of a step, like a square wave function, where it stays at 0 for 1 second, goes up to 10 volts, stays at 10 volts for 1 second, and then goes back down to 0 volts and stays there for 1 second. So if I right click on my voltage source and go to advanced, I'm going to change the function to be a pulse. Okay, we actually can configure this voltage source to behave in many different ways, which is actually really cool from a circuit modeling point of view. I'm going to set it to be pulse. V initial. V initial is what's the voltage that this voltage source is going to be providing at time 0. It's going to be 0. Okay, V on. When the voltage is on, what voltage do we want that to be at? Well, we want it to be at 10 volts. So I'm going to put a 10 in there. Base units voltage, V. Okay. Time delay. Okay, this is the time that we're going to wait before the pulse goes up. I'm going to set that to be 1 for 1 second. Okay. The time for this to rise. How fast do we want that transition from 0 to 10 volts? Now, it can't be instantaneous. If it was instantaneous, it would be 0 and 10 volts at the same time. That doesn't make any sense. It has to take some amount of time, definitely less than a second. Let's go ahead and let's make this 1 nanosecond, 0.00, well, let me just type in 1N for 1 nanosecond. The time for it to fall, I'm also going to make that 1 nanosecond. Now, for comparison, one is 1 second. 0.001 is 1 millisecond. 0.000001 is going to be 1 microsecond. Point zero zero 1 microsecond, and 1 nanosecond. That's a really fast rising pulse. I actually do have some esoteric, very weird special test equipment at home that can generate a fast rising pulse within 30 picoseconds, which is really, really fast. Generally speaking, the digital logic circuits that you've worked with, they all have rise times of like 10 nanoseconds, 15 nanoseconds, around there. I want that change to be as instantaneous as possible, so I'm just going to go with 1 nanosecond and call that good. Okay, the next setting that we want to do is our time on, T on. Yeah, you can just either or, 1N or 1 nanosecond will both be correctly recognized by the software. But realistically, the base units is in parentheses or in brackets right next to that, and so that's what the default unit is, seconds. So if you type in 1N, it's going to know that you're saying 1 nanosecond, but it will also accept if you type in NS. So either or would be valid. Okay, the T on, that's the time that we want this pulse to remain in its on state. When it's on, it's going to be at 10 volts. We want that to stay at 10 volts for 1 second. So let's go ahead and let's type in 1 for the time on. Okay, let me see if I can actually zoom in on this so that we all get the settings of this pulse. Okay, so hopefully that should be visible now, and I'll give you guys a few seconds to get this figured out. So you want to go to the advanced tab. You want 0 for the time, for the voltage initial. For V on, you want that at 10 volts. For the time delay before it goes to V on, you want 1 second. For the time it takes to rise, you want 1 nanosecond. And for the time to fall, you also want 1 nanosecond, and the time that this is going to remain on is going to be 1 second. So let's see what this pulse is supposed to look like, and then we'll see what it looks like in the simulation. Okay. V initial, 0 volts. V when it goes on, 10 volts. The time delay before it goes on, 1 second. The time to rise, 1 nanosecond. The time to fall, 1 nanosecond. The time that we remain on, 1 second. Now, those are all the parameters that we gave. But I want to see what happens after here as well. Now, the way we're going to do that is we're going to set our simulation time to stop after another 1 second. So our total simulation should run for 1, 2, 3 seconds. So after you get your pulse set up, let's go ahead and either go to Edit Simulation command, and set your stop time to be 3 seconds. Hit OK. Oh, I lost in trying to enlarge it, I lost my desktop. Let me see if I can bring it back. Don't mind my screwy screen. This is like having 2 mirrors looking at each other.
You should do that infinite mirror thing where you can see yourself like smaller and smaller on each screen.
Oh, I think I'm going to have to delete it and then add it again. Oh, maybe I can do stretch to screen. Oh, great. Okay, I found a button that says stretch to screen. Okay. So now at this point, let's go ahead. Let's run this. All of our settings should be right. Let's go simulate run. And now I want to see if I got that pulse set up correctly. So I'm going to just do a voltage measurement right above the voltage source here. And sure enough, you can see the green line. 0 volts till we hit 1 second. At 1 second, we rise up to 10 volts. We stay at 10 volts for 1 second, and then we come back down in 1 nanosecond. And then we stay at 0 volts for another 1 second. Okay, so your screen should look like this. Okay, on the waveform, show the voltage applied to the circuit. We already did that. Take a voltage measurement above your voltage source. You're going to get that 1 second positive pulse that starts at 1 second and ends at 2 seconds. Show the current through the inductor. Okay, now remember, we're going to go back to what is the whole purpose of this. Remember, an inductor is going to oppose the instantaneous change in current. Lulu, just go ahead and go to simulate, edit simulation command, type in 3 for the stop time. Okay, so as I said, the inductor is going to prevent the instantaneous change in current. So if I bring up the current on the waveform, if this was just a resistor, I would expect the current to change instantaneously. The current would change with the voltage. But given that this is an inductor, and we're going to get that self-inductance, where as the current increases, the magnetic field increases. As that magnetic field increases, a voltage is induced in the opposite direction that opposes the flow of current that caused the magnetic field to develop in the first place. That whole long story of self-inductance. As soon as I probe over my inductor and my current measurement changes to that red arrow, if I left click on this, we should not see that change instantly. It should follow that universal time constant chart, and it should follow that it takes 5 times the L over R time constant in order to reach our max value. Well, there you go. Okay. So now you can go ahead and if we probe our current, so all I did was left click on IL1. Now I can hover over here and I can take measurements as the current increases. Okay, so as current begins to go through the inductor, all of a sudden that current creates the magnetic field that induces the voltage, the back EMF. What step do you think you missed? I don't have the green. Hover over the voltage source over here and left click once. If it just shows a straight line, then that means you didn't set up your voltage source as a pulse. Okay, so I'll help out people individually. Let me get through what we're going to do in this lab now that you have the simulation running. So calculate the following: max current through the inductor after fully storing energy in the magnetic field. Well, once there's no magnetic flux changing, once there's no magnetic field that's either collapsing or expanding, that inductor just behaves like a wire. So the only thing limiting the current through this is going to be that resistor. So go ahead and calculate what the max current would be. It would just be 10 volts divided by the resistance. You're just applying Ohm's law there. For the L over R time constant, well, what's one time constant equal to? Take your inductance, divide it by the resistance, and you'll get a value. That value is in seconds. How many time constants until you reach the max current that you calculated in this first line? Well, it's going to be 5 times the time constant. And then energy stored in the inductor at max current. I gave the equation on how to do that in the first Introduction to Inductors lecture. Okay, over here, we have LR time constant in this graph. So we have 5 time constants till we reach the max current. So in fact, this third question was answered in my table. The percent of max current, that comes from the universal time constant chart. The 60%, 80%, etc., etc. The current at each time constant would be this percentage times the max current, and then the measured current at each L over R, so at each time constant, you'll grab that from the waveform in the simulation, When I say measured, I'm referring to a measurement from LT Spice. So when you go over here, your time constant that you calculate, it takes 5 time constants, 1, 2, 3, 4, 5, to reach 100%. So once you calculate what your time constant is, start at 1 second. 1 second plus that gives you the first measurement. 1 second plus 2 time constants gives you the second, third, fourth, etc. Okay, so that should get everyone started or almost finished. So go ahead and work on that. I'm gonna pause I'm gonna stop the recording at this point, and if anyone's having trouble getting these waveforms up on the screen, I'll go ahead and help you guys out individually.